Polar bears and polar cubs, it's an exciting time. It is limiting reactants. We've been looking forward to this all year long. So, why have we been looking forward to this? Well, limiting reactants kind of tells us, hey, how much of a product or how much of something can we make given the quantities of the reactants we have? And you're never going to have a perfect world where everything you have in the reactant side makes something in the product side. You're going to have something left over. And with limiting reactant, we want to know how much of that we have left over and who, aka the limiting reactant, stops the reaction from going any further. So, how do we do it? Here's kind of our list of what we should do. Step one is you need to have a balanced chemical equation before you even get to the list. Most important step, balanced chemical equation. Number two, we're going to be able to do whatever we can to find our limiting reactant, or our LR. We're going to call it LR. And then we're going to find our excess. So you're going to be able to find out how much is left of our ER. Okay. And then you should be able to, I'm sorry, that's the EX, excess. For excess, and then you should be able to actually find out how much is produced. So we can find out on the other side how much product is produced. And then finally, we're going to be able to do percent yields. Percent yields are how chemists determine how efficient a chemical reaction is. So efficiency in chemistry is due to percent yield. So how we in our class are going to calculate limiting reactants, we're going to do something called a T-chart. So how you set up a T-chart is you're going to convert all your reactants to moles. You're going to use those coefficients then in front of the reactants to create a mole ratio, and you can convert from one reactant to the other and then the opposite reactant to the first. So what you're going to do is you're going to be able to compare the mole values of the reactants. Then you're going to subtract them, and whichever one has a negative number is your limiting reactant. It's nice and simple. Does it take some work? It does. Then we have B. So you can take your theoretical yield. So this is determining how much is left over. So you can have your theoretical yield is how much when you take your LR and convert it to your product. When you subtract the other side of your T-chart, you should have a positive value. And if you take that back to grams or to whatever unit it started in, you can find out your excess. And then finally, C, percentage yield, you're going to take your actual yield, which is what we would have been given to you. Okay, and then your theoretical yield is what you determined times 100, and you're going to get your percent yield. So let's try one. So first and foremost, we want to make sure that we balance that chemical equation. In order to balance that chemical equation, all we need is a 2 in front of hydrogen. So how we set up the T-chart is we're going to put our reactants at the top and include their coefficients. And then we're going to make a T. So within the T, now we have to convert to moles. So you're going to take your givens of your reactants and convert them to moles first and foremost. So you're going to take 152.5 grams of CO over 1, and we're just going to convert it to moles, which you guys all have done before. And the molar mass of that is 28.01. Now, when I do a T-chart, what I like to do is I like to keep five digits inside of my T-chart. Okay, all of the values that go inside the T-chart, all the values that go inside here are going to be moles. So when you take 152.5 and divide it by 28.01, you are going to get 5.4444, and that's going to be moles. That's the moles of CO. That is how many moles you have of CO. Now we're going to do the same thing, but with hydrogen. So we're going to start out and we have 24.50 grams of hydrogen. You're going to then going to take that amount and you're going to multiply it by 1 mole of hydrogen gas per 2.02 grams of hydrogen gas. When you do this, you're going to get your value of hydrogen moles. So that is 12.128, and that is the moles of hydrogen that you have. So now what we do with the T-chart is we're going to take the moles of hydrogen and we're going to calculate how many moles of carbon monoxide would it take in order to use up all of that hydrogen. So how you do that is you're going to start it out with 12.128 moles of H2 over 1. Now we're going to use the molar ratio and we're going to go from moles of H2 to moles of CO. And this is a 1 over 2. So now we're going to take 12, we're going to divide it by 1, and we're going to get a total of 6.0640 mole. So right now, if I were to subtract, okay, you would notice that I would have a negative number on this CO side. So right now, we already know this is going to be our limiting reactant. I don't have enough COs. I only have 5.4444 moles. And in order to use up all of my hydrogen, I need 6.0640. I don't have that. So I'm going to use up all my COs, but I'm going to have some hydrogen left. Now we're going to calculate how much really hydrogen we need to get rid of all the COs. In order to do this, you're going to do the same kind of premise. You're going to take 5.444 moles, and that's of CO. I'm going to put that over 1 times. Now we're going to go to hydrogen, so it's 2 moles H2 over 1 mole CO. So you multiply by 2, and you get 10.888 mole. So let's go ahead and subtract it. I know that we already said, hey, CO is going to be our limiting reactant, but we subtract it on this side, we're going to get negative 0.6196. So what this tells us is that we were about 0.6 of a mole away from being able to use up all of the hydrogen with CO. On the other side, when you subtract it, you get 1.24. Now, that's how many moles of H is left over. So when you subtract them, if it's negative, you went into debt in order to use them all. Use all of the other reactant. And we can't go into debt in chemistry. So if you have a negative, it's the LR. If you have a positive, that is the excess. Well, now the question becomes, how do I calculate how much of CH3OH I would be able to produce? What do I do? Well, in order to do this, you are going to take the mole amount of the limiting reactant. So you're going to take this mole amount right here of 5.4444 moles of CO. You're going to put that over 1, and you're going to convert it to grams of CH3OH. Well, the very next step is the mole ratio. And then we go to grams. So the gram molar mass of that is 32.05. Mole ratio is 1 to 1. So really what happens is you're going to take 5.4444 and multiply by 32.05. And you're going to get a total. Remember, it's 4 sig figs because the given of CO right here is in 4 sig figs. So your final answer will be in the number of sig figs your given was in. And it was 174.5 grams of CH3OH. And this is the theoretical amount. So let's continue with this problem because we're not done. Okay, we've calculated the theoretical. We know who the limiting reactant is, but there's a lot more information that we can determine. So the next question asks for how much excess is left over. So in order to do this, we go back to our T-chart and we find out that positive mole value, which was 1.24 moles. And we're going to start with that. So we'll start with 1.24 moles. Now remember, this is of hydrogen gas. We're going to put that over 1. And all we're going to do with this is multiply it back up to the grams. So what you get is times 2.02 grams of H2 over 1 mole H2. And you multiply that, and you get about 2.50 grams of H2. Now, with that, there's a nifty little trick to make sure that you have kind of the right numbers. Due to the law of conservation of mass, the mass that we start out with is equal to the mass that we end with. So if you take 74.5 plus the 2.5 that we got left over, it should equal the total at the top. So if you take 174.5 plus 2.5, you get 177.0 grams. That's the mass that we have left or produced of our product. If we come up to the top, we need to take 152.5 plus 24.5, and let's see, 0.0. The 1 comes up here. That's a 7, 7, and 1. Wow, look at that. 177 and 177. And I promise you, if your math is done correctly, that little trick works on every limiting reactant problem due to the conservation of mass and matter within the world. So we have one last thing to do. We want to see how efficient this reaction was. Well, Mr. Madej and Mr. Carneal were in the lab. We were running this reaction, and we determined that really we only got 170 grams. So you have 170 grams, and this is the actual. Based off of how much we could get, it was 174.5. This is the theoretical. So in order to determine how efficient it was, you're going to take the actual divided by the theoretical and multiply by 100. So we're going to take 170.0 divided by 174.5, and we're going to multiply it by a nice 100, and we're going to get a percentage. Remember, percentages, we're just going to keep to the hundredths place, and we get 97.42%. That's a great efficiency for a chemical reaction. A lot of chemical reactions within the world only really produce at about a 70 to 75% efficiency unless catalysts and things like that are within its presence. All right, polar bears and polar cubs, that is LR. Go ahead and try that worksheet. Let me know if you have any questions. This topic really does take work and kind of writing it out and making sure that we show all our work every single step of the way. Best of luck.